My name is Yuzhu-Lu. I work on front-end 3D graphics. So today I'm going to give an overview of 3D graphics in front-end and also talk about some of the new stuff, what we're working on currently. And as you know, we have a very rich set of 3D primitives, directives, and options. These are the best components for all 3D visualization functions. And these in blue are newly introduced in version 10. And we will keep adding to it. But today I'm going to let you take a little bit closer look and see what's behind the scene. For 3D graphics, we have 4 rendering engines. And I'm going to use this example to compare between them. There are depth buffer, depth peeling, and BSP tree and software. Depth buffer is a default method used for non-transparent object rendering. It is using the, as the name shows, it is using the depth buffer for depth computing. Because it's using the hardware, it will be very fast and use less memory. It is available. It is always available. But the downside is it might have some z-fighting issues, like over here. So then what is z-fighting? It is caused by the depth precision. When, assuming there are 2 coplanar polygons there, we need to do a pixel for depth computing for each pixel. Because of the computing error, some of the pixels were on top of the other surface. Others are not. And that caused the z-fighting issue. If you improve the precision of the depth buffer from 24-bit to 32-bit, which is supported on some of the new hardwares, it might improve it a little bit, but cannot totally remove that because it comes with the depth buffer. So the good solution to that is trying to avoid the coplanar by adding a small offset to it. So let's talk about the depth peeling. It is also using the depth buffer. What the difference is, it is a multiple rendering pass method because of the transparency. Because using the depth buffer, it's fast, it's used less memory. It will be available on most hardwares and drivers, but might not on some very old computers. Because it's using depth buffer, it will also have the z-fighting issue here. BSP tree is a different method. It split all 3D polygons into very small sub-triangles and try to sort them before rendering it. Because of the splitting, it will take a lot of memory compared to the depth buffer. And because of the BSP tree construction and also the sorting, it will be slow. But it is available all the time. It will not have the z-fighting issues, but it has its own artifacts. The mesh line will look very dashed. Why these artifacts coming from? It is also because of the precisions, the computer errors. I mentioned that polygons will subdivided, and the lines will be divided into sublines as well. So they are supposed to be on the top of surface, should be coplanar with surface, but because of computing errors, some of the sublines were on top of it, some of them were not. That is why it is look dashed. It might also have some stitching issues because of splitting. But the main issue is the memory. It might cause crash in some cases. Software, it is also using BSP tree. What it is different is it will project all 3D objects into 2D objects and then draw all the 2D object. So because it's also using BSP tree, it will have all the downside from BSP tree. And other than that, because of the projection, it will be even slower. And because of it is using 2D drawing layer, it might have some features not supported, like texture. In this case, the texture is not showing up. But it is good to know the downside for each rendering engine. So you can choose the right one if you have different needs. So you might want to ask why we still need a software case. Well, there are some cases like the driver or the hardware doesn't work very well. And if this happens, the software can be a choice. And about the depth peeling availability, there are some flags in the system information you can check. And if it says here true, it means depth peeling is supported. So by default, the depth peeling and depth buffer will be used. Okay, so color buffer and depth buffer. Color buffer is usually what you see as a random result. It contains the color value for each pixel rendered. And the depth buffer, as I mentioned before, is used for depth computing. But you can also choose to visualize that. Like in this example, if you rotate the viewpoint changes, the depth value changes as well. So let's think about there's an example. Let's say the object is there, the camera is there. It is looking in this direction. When these lights go into the object, it will first hit the first layer of the object, and then the second, and then the third. And you can choose to visualize these different layers. With these different layers, you can have a better understanding about what structure it is. And if you combine those different layers together in order, you can get a very good transparent result. That is how depth peeling works. Precisions about the color buffer. There's 4 choices you can choose right now. 8-bit is usually used by default for all primitives, except the rest 3D. But you can also choose the high bits for your needs. Here's the example. I don't know if you can see it clearly here. I set the voxel value to a very small color, and it is not received very well in the 8-bit, but it works well in other high bits. There's another example. You might see it better. If I can try to change it to a even smaller value, and you will see even for high bits, there's some difference there. So high bits means more precision. Okay, now I'll talk about some new stuff what we are working on. From time to time, I got users come to me and complain that assuming we have a very large data set, we know it is static. It does not contain any dynamics in it? Is there any way to optimize it, at least to make it responding to interactions? Now we have the method option. You can optimize it. What it does is just try, because it knows it is static data. So what it does is try to reuse the data on the hardware instead of keep pushing data to the hardware and through the way. Then I want to show you a data set. This is from a user. The data set is resampled from the real-world data. But still, it contains 500,000 polygons there. So this is without the options setting. And you will see it is not really responding. You can see the frame rate is just about 2. I'm sure you were not satisfied with that. So, but how about try the option? For the first time loading, it will take almost the same time. But once it is loaded, it can render much faster because it can reuse the data. You can see frame rate goes up to 35, 36. So it is almost 20 times faster. Okay, I want to talk about another issue. Like assuming we are going to make a very nice camera fly-through animation like the Google Earth does. So you have a very decent 3D models. You have a very large texture. It contains all the details so that when you look closer, it shows up very good. But in some view angle, it looks very bad. It has artifacts. Why this happens is because the texture is big. There exists some cases like when doing the texture mapping, it will map the whole area into just 1 pixel. But the hardware can only do 1 pixel sampling. That is why the artifacts coming from. The solution is to use mipmap. How it works, it just automatically generate, when the application push the data to the hardware, it will automatically generate a set of downsized duplicate of the main texture. So the hardware can choose the right texture to look at based on the viewpoint, and to avoid the multiple, to mapping multiple texels into 1 pixel. I want to show you the example here. It contains a texture of this texture size itself is 110 megabyte. It is huge, and for each channel, it contains 8-bit. It will take about 30 seconds to come up. Most time spent on, let me do some multitasking and save some time. I'm going to try to compare the version with mipmap and without mipmap. Let's see if that pops up. Not yet. Here we go. Try to evaluate this one. We will see here. Here, there are a lot of aliasing artifacts there. And if It will coming. Yeah. Let's compare them side by side. There's no, you mean the mipmap and without mipmap?
What's the difference in the two commands?
There's actually,
They're identical, right? It's just
the commands they are totally identical. What's the difference internally? I turn the mipmap on and off. It's by some OpenGL implementation.
But this is an unreleased front end that we're looking at, right?
Yeah, this is not released yet.
So this would be basically automatically turned on?
Yeah, it is turned on, but
Once we ship the technology.
yeah. But if you want an option, we can add an option for that to turn it on and turn it off. So you can have a better idea. I can try, but this, if you assume that it will become larger, you won't have the mapping multiple pixels into one pixel case. So it will be different case. Last, I want to talk about lighting on raster 3D. Lighting on raster 3D isn't easy because raster 3D is a little bit different. It does not contain any geometry information like polygons and normals. So to make it work, you need to compute normals for each voxel by the color gradient values, and also do the computing for each voxel, do the lighting computing for each voxel. With this option, you can have, there are 3 different choices. By default, it is turned off, but you can turn it on. What's the difference between true and the enhanced agent? This option will do extra work and try to remove some of the background noise and try to enhance the key features by multiply the alpha channel with the magnitude of the normal computed, the gradient values. Here's a comparison. Here, you will see without lighting, you won't see much details. But with lighting on, you can get a much better depth perception. I want to try a different color function. This one is used as a default color function for image 3D. I want to show you the difference between the normal lighting, and I can also change the specularity. So here, some of the noise is removed. Like the part of neck, you can visualize more details. Rotate it, yeah. You can also zoom in. So you can pan it. Now, here, this is the value. This is used for the default. For image 3D, it is encoded in the C code, but you can also make it yourself. Here's the example. This is a explicit one. And with the same data set, you can choose to visualize the internal structure. And you will see with the depth perception, there are more details instead of just flat. And you can zoom in. And considering the job it is doing, 45, 46 frame rate is pretty good.
And can you do exactly that on the first one, the one that's not lit?
This one is a little bit art-like style, but in some cases it will look flat. We implemented the lighting for all cases, so it will work any combinations. Here's an example of spot lighting. And point lighting, bunch of point lighting. So anything work with polygon will work with raster 3D now. So yeah, that's my talk.